In this second video of our periodic trends unit, we are going to be looking at families on the periodic table. Yet another way that the periodic table satisfies periodic law by grouping together elements that have similar chemical and physical properties. Families are smaller groups than the metals and the nonmetals, but again, these elements in these smaller groups have chemical and physical properties. Group 1 on the periodic table are called the alkali metals. Alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Everything in that first column with the exception of hydrogen, as I mentioned in the last video, as we learned when we talked about types of elements. Hydrogen is over there in group 1, but it's not a metal at all. It is a nonmetal. It's only there because of its one valence electron. So group 1 on the periodic table are the alkali metals. All alkali metals have the following properties. They form, and hey, look, I spelled it right, +1 ions when they react. They have low melting and boiling points, much lower than what you would expect from a metal. For example, sodium melts same as the boiling point of water, about 200 or so degrees Fahrenheit. Not what you would expect of a metal. They're soft metals. You could take sodium and literally cut it with a butter knife, and they react very vigorously with water. They become downright explosive when you put them in water. Again, not a typical behavior you expect from a metal. Our next family is group 2. Beryllium, magnesium, calcium, strontium, barium, and radium. These elements in group 2 are called the alkaline earth metals. This time it's all of the group because they're all metals. And again, the alkaline earth metals all share a number of common properties. They form +2 ions when they react. So your alkali metals, group 1, make +1 ions. Your alkaline earth metals, group 2, all make +2 ions. They have higher melting and boiling points than what you saw, what I told you about in your alkali metals. They are harder than alkali metals. They will react vigorously with water, but only under certain conditions. So, for example, you can take a chunk of magnesium and put water on it, and nothing exciting is going to happen. However, if that magnesium were burning extremely hot and you put water on it, then it can become explosive. So whereas if you take a chunk of sodium, Na, and put it in water, it'll fizzle, spark, it can burst into flames. If you put water on just regular room temperature magnesium, nothing's going to happen. You have to get that magnesium hot, it needs to be burning in order for it to do anything spectacular. What you're going to see here is a progression as we move across the metals. Melting and boiling points increase, hardness increased, this reactivity of water decreases, and that continues on into our next group of metals, groups 3 through 12. So that big D block in the middle. They're called transition metals. And again, we're going to see the changing of properties. We're going to see the melting and boiling points get higher still. We're going to see the hardness increase. And we're going to see the reactivity with water decrease even further. In addition to that, they form more than one ion. So whereas group 1 always makes a +1, group makes a +2, groups 3 through 12 can usually form more than one ion. They can be +1, +2, +3, +4. There's some variety in there. That's going to be to us when we get into our ionic bonding unit. Now we jump over to the nonmetal side, all the way to the other side of the table in group 18. Helium, neon, argon, krypton, xenon, and radon, those are the noble gases. Noble gases have two significant common properties. One, they're all gases, thus the name. And two, they don't react with anything in nature. They don't interact with the other elements, thus the name. They were called noble gases because they were like the nobility of the periodic table. They don't relate with the commoners. They don't interact with the commoners. They kind of just stick to themselves. They're perfectly stable. Talked about this before. This is why helium is over on that side of the table. Helium doesn't react with anything in nature, and it is a gas, so it's put over there with the rest of the noble gases, even though it has two valence electrons, even though it really belongs in the s block. Move one column over to the left to group 17, fluorine, chlorine, bromine, iodine, and acetine. You've got the halogens. They have a little bit more in common. The halogens all make -1 ions when they react. So negative charge this time. They're all diatomic elements. You never find a single atom of these elements in nature. These are the most reactive of the nonmetals. They are so reactive that you never find a single element in nature. In other words, there's no such thing as a single fluorine atom in nature. It's always bonded to something else. And if it's not in a compound, if it's an element, it'll be another fluorine atom and its formula will be F2. Same with all the rest of the group. They are very reactive. Again, they are the most reactive nonmetals. And they form compounds called salts when they react with metals. Must have slowed down a little bit when I typed this section. They form compounds called salts when they react with metals. So when sodium and chlorine combine together, they form a salt we call table salt, stuff we put on our French fries. Whenever anything from group 1 reacts with something in group 17, you make a salt, just different kinds of salts. So again, everything you see that dark green color, those are your alkali metals. Everything you see in that aqua type color, those are your alkaline earth metals. Your purples are your transition metals. Your blacks are your noble gases. Your red ones are your halogens. You'll note groups 3 through 16, no single color there. We'll talk about what that means. And you'll see the two rows across the bottom of the lanthanide and actinide series. Those are in green. We'll talk a little bit about those as well. First groups 13 through 16. Those ones that are several different colors. Those are often called mixed groups because they're a mix of metals, nonmetals, and metalloids. Because they're a mix of metals, nonmetals, and metalloids, they don't have common properties. So we really don't give them family names because there really are no families there. There are no common properties in those groups. They don't form common ions within those groups. They don't react the same way within those groups. There's really no true families there. Sometimes groups 13 through 16 are broken down into single columns named after the element on top. For example, sometimes group 15 is called the nitrogen family, sometimes 16 is the oxygen family, but again, they're not really families because they don't have common properties up and down that group. The nonmetals will have some similarities in that group. So within the nitrogen group, nitrogen and phosphorus are pretty similar. The metals in the group will have some common properties. So tin and bismuth will have some common properties, but the properties of nitrogen and phosphorus are not the same as the properties of the actually antimony and bismuth. So again, they won't have common properties. So they really aren't families. And so the two rows across the bottom that were all in green, those are the lanthanide and actinide series. They're sometimes called rare earth metals, but that's kind of a misnomer. They're not all rare. There's some that are relatively abundant. They got the name rare because it was difficult and tedious and costly to purify them. So you never found a lot of them available to purchase. At least back when they were first discovered. Now things like neodymium are much more common and much more readily available than what they used to be. Again, their properties aren't very consistent. They're not really true families per se. And this is because they're a mix of lighter and heavier metals. The lanthanides, those are cerium through whatever Lu is, 58 through 71. They're relatively light with masses that range from 140 to 175. The actinide series, thorium through lawrencium, 90 through 103, are considerably heavier, 232 to 262, if I'm reading that right, from across the room. You know me and my glasses. You have heavy ones, you have light ones, so the properties tend to be a little different between the two groups. We can say most of the lanthanides are magnetic. That's where neodymium is. Some of the strongest magnets in the world are neodymium magnets. Most of those are magnetic. It's really only three in the main body of the periodic table: iron, cobalt, and nickel. The rest of the magnetic elements are found in the lanthanide series. And we can't say all the actinides are radioactive. So 90 through 103, all of those elements are radioactive elements. But that's really all we can say about them. Again, not a lot of common properties down there because they're, again, kind of a mix of two different types of elements on the bottom. So that's the end of this one. In the next video, we'll start talking about things like electronegativity, ionization energy, and electron affinity.